My name is Siu Fai Leung. I'm the department head of the Department of Economics, and today I'll be the host of this talk. And the talk is on the integrating innovation and climate with economic growth, about the 2018 Nobel Prize in Economic Science. So as you all know, the Nobel Prize in Economics this year was awarded to William Nordhaus and Paul Romer. So for their contribution in integrating innovation into growth, and then for William Nordhaus, integrating climate into economic growth. So we'll have two speakers on these topics. And the first one is by Professor Wang from Economics Department. And he will talk about climate change. And then after he finishes presentation, it will be Professor Z on the innovation and economic growth. So then we'll hold the questions until both of them finish the presentation. So let us invite Professor Wang to come and then give the presentation.
Thanks for coming. It's a great pleasure to summarize the contribution of Professor William Nordhaus. And his contribution is recognized by the Nobel Prize Committee is to endogenous climate change. So this is all clearly that a very important and urgent challenge that is faced by the whole humankind. And economics offer us a powerful tool to study that what are the remedies that we can make to revert or change the climate increases trend. So this is the basic of Professor William Nordhaus' contribution. So that is this I actually aside from that integrate climate change into a long-run macroeconomic analysis. Professor Nordhaus was a PhD student from MIT. He graduated in 1963, and you can see that his advisors are all the giants in economics. So one of them, Nobel Scholar, he got the Nobel Prize in 1987, and another is Paul Samuelson, is one of the founders of the modern economics. So he got the Nobel Prize in 1970. Actually, Professor Nordhaus was an undergraduate from Yale University. During Yale, he also was supervised by another Nobel Prize laureate, that is Thomas Tobin. And then he started his career at Yale. You can see that recently that Yale, a lot of Nobel Prize laureates in economics are associated with Yale at some time during their career. So like Stiglitz, this is 2001, and Schelling, and recently you can also see that very recently that is Holmström. The reason I'm making that, you can clearly see that there are some positive spillover among ideas. Great minds think alike, so they generate a lot of positive spillover. But unfortunately, so does pollution. Yeah, so pollution on the other hand side generate a very important negative externality. I think the positive externality will be more elaborated by Professor Xie in recognizing Paul Romer's contribution. So my talk will focus on this one, the pollution. There are a lot of studies, although there's a lot of also debate. I have to say that after reading the literature in the recent few days, the consensus is, the majority is think that the global warming is real, and the consequences are very severe. So also that there's a widely consensus that our human activity have contributed a lot to the recent global warming. So, for example, that in the last century, the human activity have contribute about 1 to 1 degree increases in the global climate. And this one we like to continue. You already probably see a lot of pictures. I didn't post those pictures in my lecture. You can see that a lot of iceberg meltdown, and the polar bear floating in the middle of the sea. So that is the vivid illustration of this global warming. If you want to say that, if you want to prevent that, if the climate change increase further, say by 2 degrees, then there will be disasters. And if you want to do that, there was also a study by the recent national, United Nations, that you have to cut down this CO2 emission dramatically by 40 or 60%. So this will be a lot of effort have to make. This is from a natural science perspective. This is the goal, but why economics is important? Why we think economics is useful and important? Because in order to achieve this goal, there could be many different policy or different paths of emission, and there we have different economics benefit and cost. If you want, suppose that you want to stop the CO2 emission, you can shut down all the factory that are still using, say that in China, using coal instead of other clean energy. But clearly, that will be an economic disaster, at least in the short run. So also that this market, individual in this market will not automatically say that we all agree, human can agree that we have to cut down this emission, but we always will tend to say that why not let other people to do the job? I still enjoy the benefit of a luxury or lifestyle with a lot of energy consumption. So the market will not do that. So we have to think about properly that what kind of policy interventions, what kind of policy can help us to achieve that, either through the tax of this CO2 emission, or through some, say that quota, tradable quota systems. And what will be the consequence of those policies are not clear. Also that even you think about that tax is desirable, then there's also another question. Who should pay for the tax? You see that this global warming is a consequence of 300 years of emission after industrial revolution. But a lot of developing countries, they were still in the agriculture society during the past, say that 200 years. And now they are catching up with the industry country, try to industrialize, and then they start to use this modern technology. They create this CO2 emission. Should those countries pay the cost, or the industrialized country pay the cost? So those are the open questions, and only I think economics tools can give us some perspective. That's why I think economics is important in this one. For example, there's also actually a lot of skepticism. So one group of scientists once proposed that, so let's wait for another 50 years. We don't do nothing. We do nothing except that the policy already implemented. So if we do so, there are clearly advantages, because one of the arguments is that you could, by doing that, you could allow that less developed country to be more easily catch up with a developed economy. And 50 years later, maybe we have better technology in other clean energies. There's one argument there. And they also make some things. But the cost is we might get more emission, and there might be a chance that you hit the threshold, and then you probably have like a disaster consequence, like the sea level rise, and more intense hurricanes, and a lot of loss of species, and the damage to these ecosystems. So there's the cost there. So if you want to refute this kind of argument, you also need an economic model. Say that in a model that we can, because we cannot wait, we have to do this sort of experiments. We cannot do experiments for this type of question. So that is why you have to rely on a model. And of course, this model have to be rich enough that can capture the historical pattern of, say, that climate change. And also you can capture the historical economic development pattern. So that is a important and also not easy task. And this is one of the contribution for Professor Norhaus. He was the first one to propose a unified a model to help us to answer this kind of question. So in this type of model, this is now we call this integrated assessment model. So the integrated assessment model actually integrate the model that already developed by the climate science, the scientists in the climate studies, and also economic model. And this model, the minimum requirement, you have to have 3 parts. First of all, we have to know that how this carbon concentration in the atmosphere depends on economic activity. So if the carbon concentration are measured, say that a non-human, a result of non-human activity, then even there's global warming, there's nothing we can do, right? This is, if that is purely a result of natural process, human beings have little to contribute. Even that the danger is severe, but you can do little. And if that carbon concentration are mainly a result of economic activity, there's something we can do. So this is the first part. We have to understand how this carbon concentration depends on economic activity. Another one is how this carbon concentration affects global temperature. So this one we can simply borrow from the natural science, because the climate scientists have developed a very sophisticated model. They include like thousands of equations, thousands of variables that can give you a prediction of how carbon concentration affects global temperature. And we have to understand how economic activity and human welfare depend on global temperature. Say that this global temperature might create a atmosphere disaster, might reduce the productivity, or damage some of the buildings, or damage some of the infrastructures. So this one we can also incorporate by looking at the past, so that this temperature increases. What is the chance of increase in hurricane? What is the chance of increase like extreme weather? So those are the 3 elements. But you have to do a little bit simplification. Yeah, economic model, you have to keep the model that manageable. In climate science, the people can do like thousands of equations. It's not a problem, because in natural science, the particle movements are purely deterministic, or sometimes might be subject to some random shocks that we don't understand yet. But the particle pure action are purely backward-looking in sense that the expectation of future does not affect their behavior. But the humankind, on the other hand, most of our action depends on our expectation about the future. So the causality run in an opposite way, often that the future is the cause and action is the consequence. And if you can cover into that, then this means that all the existing activity will be a function of the so-called states variable. So if you introduce like thousands of equations, you will throw in thousands of states. And how the states variable evolve over time, again, will depend on the expectation of people's activity. So that will be a very daunting task. And that's it kind of complication force us to look at a simple version of the climate science model. So for this part, so you have to keep this manageable, but of course you have to keep it rich enough so you can satisfactorily capture the historical pattern of climate change. So this is the integrated assessment model. Of course, there's some latest development that we talk about later. So the latest development that you become more sophisticated, and this model become richer and closer to capture the reality. But the time when Professor Neuhaus proposed this kind of integrated assessment model, the computation of a computer is still limited, and our economist's ability to handle this large model is also limited. So he keep this model simple, yeah. But these have to be, I already said that, have to be dynamic, forward-looking. So I already said that, so I'm going to skip that. So what is an element of his study? Okay, I said that is three parts. The first part is you borrow from the natural science. So how carbon concentration affects global temperature. This actually is fun for me to learn. I'm not familiar with this either before I agreed to present Professor Neuhaus' scientific contribution. Basically, in the climate science is that the temperature will rise if that the Earth's energy budget increases. This energy budget is the net of the energy we receive from the solar system and our reflection back to the space, and this depends on a lot of on human activities, also non-human activities. So human activities by like burning of the fossil energy. So we create this CO2 emission, so if basically that if this one increases, the energy budget increases. There's a famous equation. The guy who proposed this equation also got the Nobel Prize, not in economics. Basically, that if the energy budget double to some baseline energy budget, the temperature will increase by like 2 degrees. And this temperature also depends on, because a lot of this absorbing, when we increase this CO2 emission, some of this emission will be absorbed by the ocean. So that's why ocean's temperature is quite also important. So basically that you have to track of the ocean temperature, the temperature in the atmosphere, and this Earth's energy budget. And then these concentrations. So this energy budget, I say that it will be affected by this emission. And so those concentrations will depend on the upper level of the sea, ocean, and deeper level of the ocean. And they follow a deterministic differential equation. And those are the linear. And if you counted that, then we have like 6 state variable already. But in short, you can see that the temperature will be a very long linear function of the past carbon emission. So in short. So but this carbon emission is determined by economic model. And this will have a general feedback. So the human activity depends on the emission, and the emission will determine gradually about the temperature change. Temperature change will affect the humans' activities through so-called damage function. I will be specified soon. So that is the simple, simplified climate model. But this one already got you 6 state variable. And then the economic model part will share the similar flavor of Paul Romer's study. That is extended Sorrow model, optimal growth model, initially developed by Sorrow and many others. This is like the host. This is the baseline model in macro nowadays. Basically, that we will assume that people are fully rational. They care about not today, but also about the future. It looks a little bit odd. It's strange that people will live for infinite period, but this simply is a modeling trick to capture that we not only care about ourselves, but also care about our children's future, and our children will care about their children. So that's why a single individual will care about all the future consumptions of future generation. That's why you see this is a utility. It's sum from today to the future. So in each period, the utility will depend on the consumption and also the population. So this will be like consumption per person in this economy. And but of course, the future welfare will be discounted by a factor beta. So if beta is smaller than 1, that the future one will be discounted. If we care more about our future generation, the beta will be larger. So that is the objective. So the utility, this will be a welfare criteria for us to verify, to access different policy. So different policy, the idea is that the policy will give us the maximum of this utility flow. And then in each region, this is a model with many regions. Why? Because each region's emission alone have a little impact on the temperature. Only thing matters is the global emission. So that's why you can see that it's clearly a coordination problem there. The United States will want China to cut a lot of this emission, carbon emission. But they were enjoying a better climate. So China will also have an incentive, say that the U.S. to pay the cost, and we still keep the economic development at a faster pace. So there will be that is the source of the so-called negative externality here. So this is the budget constraint. So today's consumption will depend on, of course, the total amount of output. The total output will be produced by capital and labor, and also energy. Okay, but energy after some normalization that will proportional to the carbon emission. So basically, that the input is that you need to produce. You have to have capital, labor, and this is CO2 emission. And in different places, they might have different coefficients, but that is a detail. Okay, you can make the model. It will reach that some country using more energy more intensive, some country using energy less intensive, and each country will also have a different technology progress. But most importantly, that the temperature will affect the economic model by a damage function. And this damage function in the earlier model of Professor Norhaus is estimated to be this form. Basically, when temperature increases, you can see that this one becomes smaller. And if temperature increases more, then the decrease in output will be much larger. So you can use the past history to estimate these coefficients. Each region might have different theta, this is the feedback. So when temperature increases, then the agent in this model will understand. Okay, if I increase the emission today, in the future that will come back to me, because in the future, then the future's temperature will rise. That will reduce my output in the future. So there will be clearly trade-off between today and the future in this type of model. And also clearly that the market failure, because this temperature depends on the global emission, not my own emission. So the market force, everyone, each region will just simply make their own utility. They will ignore their effects on others. If you have this model, then you can solve the model, okay? There are several regions, in case of earlier studies like North America, European, China, India, and some less developing countries. So there will be 7 regions. There will be 7 capital stock to be a state variable, and the 7 this technology be a state variable, and also there will be like 6 state variable from the climate model. So you add together, that will be a difficult task to solve the model. But anyway, they developed a method to solve the kind of model and to evaluate the different policies. So for example, you can use this model to say that, okay, to see that the first one is if we do nothing except those policies already implemented. And another one is we look at what is the optimal path of emission. And the third one, if you are a little bit cautious, so that I want to be certainly sure that the temperature in the past will not exceed 2.5 degrees above the pre-industry age. Also, you can think about, say that if that we care about our future more, initially that its beta is discounted by like 10% each year, but let's say that the discount very slowly, care about more about the future, then what will be the path of this emission? So you can simulate that. This is the simulation for his 2017 newspaper. First of all, this is the baseline. You do nothing. Then you will see that this global emission, this is the total CO2 per tons. That way goes to this level, increase very fastly. And the optimal one, you will see that eventually that will decline. For this area, I think it captures the idea that why we still want this emission to increase over time before that the decline is a lot of countries still in a less developed stage. And if allow the emission, then their initial GDP growth will be faster. And that add to their welfare of the current generation. And eventually, but the people understanding this model, eventually when get rich, they will decline the emission. So that, but it's slowly. The third situation is that we want to for sure that the temperature rise will not be above 2.5 degrees. So you see that we see that a dramatic decline of the emission, and eventually by 2055, the emission will be close to 0. So initially you see that this is today's emission is 30, and the dramatic decline that to 10 in the next 15 years. So that is a dramatic reduction. Or that if you care about our future, so we discount our future very slowly, then this is an emission. So similar to this pattern here. We can also use this model to see that what will be the temperature, the average, say that increasing of the temperature in the future. So you see that this will be the temperature that will rise by 4 points by the next, in the beginning of next century. And this is the optimal one. You see that it increases, but there's less degree. And for the other two policies, the temperature will, because you see that it is an emission, the temperature will be, the rise will be below this 2.5 degree. So those are the earlier type of assessment model. You can do a lot of stuff there. You can, I think the latest development includes actually I read some of the paper. So one of the paper is written by a Smith. He's a professor, used to be a professor at Princeton, and now back to Sweden. I think he's one of the Nobel Prize selection committee. He is also interested in this climate change. He now developed models with thousands of regions. You not look at a country as a player, because even with a country, there's still there will be still a free ride problem. Within a country, because the whole emission, the total emission will affect the environment. So I will still prefer other people to cut down this carbon oxide emission. So he thinks that a more suitable player will be a small region. So if you look at the latitudes and altitudes of the Earth, he divided that into thousands of regions. And these thousand regions, of course, will be much richer. There are also, I think, other kind of interesting studies here. Here you treat that each country, people are the same, right? So there's no distribution effects. And the climate change definitely have a distribution effects. So some area be affected more if you like Hong Kong. We are close to the sea. If the sea rise, so that 2 meters, that the central will be gone, right? So that will be affected more severely. Other region might be benefit. Russia, for example, if climate changes increases, that will be good for them because they are close to the northern pole. So climate change will make a lot of land become more productive. Canada, for example, will benefit from that. There will be a lot of distribution effects. And even within a country, there are also distribution effects. You see that in the recent years, a lot of debate about the air pollution in Beijing. So the middle income class and the rich people will prefer a clean air, right? But for poor people, they have to make a living. So burning coal probably for them is the best choice because it's cheaper. But of course, it's not. This have interest conflicts with the middle income class and the rich class. So there are a lot of distribution effects here. So you can use this type of model to study. So who should pay for the cost? Even that we say that we agree that this total amount of emission for a certain level, but then who should pay? Should it be the rich people pay, or for the poor people pay? So I think in China, we see a lot of report that you are forbidden people to burn coal in the winter because of this emission. So anyway, I think this will be still a growing literature And there will be a lot of study have to done. By the way, that also there's a question that now in the international trade we trade commodities, but that is effective trading of emission. So if the U.S. consumer say buys, if the goods that was produced in the U.S., then the emission will be from U.S., right? That affected the U.S. This emission. But if the factory moved to China by outsourcing, then it also sourcing emission, pollution to other countries. So why should the developing country pay for the cost? Why the developed country not pay the cost? So there are a lot of issues like trade. You also trading this carbon coincidence emission. So so that I think will be a very interesting future area for the graduate students. So let me stop here.
Okay, so now let's look at the other Nobel Prize winner, Professor Paul Romer. So let me first try to motivate his study. Okay. Now, this is the chart showing the U.S. GDP over time. Okay. So what do you see? You see a huge trend upward. Okay. Despite the fact that U.S. has been involved in many different wars. You know, there are hot wars, cold war, trade war, okay? For sure, I mean, there were a lot of human suffering, okay? But what you see is the big upward trend. And also, you know, there were a number of big stock market crashes, okay? So you see wealth, you know, just evaporate quickly, right? Nevertheless, I mean, the economy recovers, okay, even after all these terrible crashes, like, you know, 1929, Great Depression, and 1987, Black Monday, financial tsunami, right, and dot-com bubble. But then economy, you know, begin to recover and pick up its pace. In fact, when Paul Romer looked at, you know, the historical economic growth, and he found that, in fact, the growth rate of the most advanced economies over time were actually higher and higher, okay? And my student and I, we extended and modified his chart, and we also show that, you know, the growth rate, this is the per capita GDP growth rate, have been on the rise, okay, historically. So how could it be possible that growth rates were like increasing, okay, even though we know that in the world there are finite resources, okay? So Paul Romer does recognize that resources are finite, okay, indeed. But he says that the pessimistic view of the limits to growth, you know, by the Club of Rome, okay, so those people who advocate that limits to growth, there were limits to growth. So this statement is wrong, okay, the pessimism is wrong. Because Paul Romer argues that the inventive ways to combine finite materials, okay, just almost limitless, okay, almost limitless. And they will turn, you know, even small number of materials into highly demanded and valuable products, okay? In the 1990s, I remember when we need to back up our data, you know, our files, we have to use this huge tape drive, you know, which is probably just can contain 500 megabytes, okay? So nowadays, a small USB drive can hold up to like maybe 200 gigabytes, okay? So that's just a huge difference. So how to explain this increasing rates of growth? At the beginning of human existence, population growth was extremely low, productivity growth was extremely low, because we were basically hunter-gatherer, and were fighting for our survival, okay? And we make progresses through genetic evolution, which usually takes 1,000 years to do a little bit of improvement, right? So then, humans learned how to control fire, okay? And also, that lead to subsequent technological progress. And when humans developed verbal language, they enhanced their coordination so they can hunt for larger animals, okay? And after we develop written language, then growth speeds up further, okay? Because we're standing on the shoulders of giants, okay? So we have written record, we can easily learn from our ancestors, from their findings. Okay, so what are the determinants of growth? Okay. Of course, when capital increases, or when labor increases, the output will be increased. Okay, but those factors typically are subject to diminishing returns. Okay, so sooner or later, the marginal contribution of those factors to growth will be limited. Okay. So it is the technological change that can lead to sustainable economic growth. Okay, sustainable economic growth. So to have technological change, okay, the two factors that we need most, one is human capital accumulation. Okay, human capital. Okay, those were emphasized by Becker and Lucas. Both of them from Chicago, University of Chicago, Nobel Prize winners. Or have knowledge accumulation. So that's the one emphasized by Paul Romer. Okay, so Paul Romer, in fact, wanted to highlight the difference between human capital and knowledge. Okay, and the difference involves two important concepts. Okay, one is called non-rivalry. The other one is excludability. Okay. So what is rivalry and excludability? Okay. Now human capital is rival and excludable. Rival means if I'm using it, then you cannot use it at the same time. Okay. So if I'm using this pilot, for example, to fly my airplane, then you cannot use it at the same time. Okay. So rivalry. So if it's non-rival, then if I'm using it, then you can use it at the same time. So that's the knowledge, right? Knowledge is non-rival. Okay. So you can use pasteurization process to kill some bacteria. Other people can use it at the same time. Okay. There's no confliction. There's no conflict. You can use a Lagrangian multiplier method, to solve an optimization problem. I could do it at the same time. Okay, so there's no conflict. So that's knowledge, non-rival. Okay, but human capital, okay, it is rival, and also it is excludable. Okay, meaning that if the pilot doesn't want to fly the airplane, you cannot force him. Okay, so you have to pay him and entice him to, or give him incentive to fly the airplane for you. Okay. Okay, so knowledge is non-rival. Okay, but some knowledge, okay, knowledge such as a piece of software, okay, can be partially excludable. Okay, meaning that if you don't have the license, if you don't pay for it, then you're not allowed to use it. Okay. Or there's some way to block you, so that you cannot use it. So even then, people can obtain insights studying the software code. Okay, so that's why we say it's only partially excludable. Okay, you can include, but there are still some elements that you can learn from that. So it is only partially excludable. And Paul Romer says that this kind of attributes, okay, the partial excludability plus non-rivalry, that is the important factors for sustainable economic growth. Okay, so partial excludability allows private effort in R&D to occur, okay, because they seek profits. Okay, so that gives them incentives to work hard and to develop new stuff. Okay, because they can benefit. They can partially block you, okay, from using it unless you pay, right? But since it's only partially excludable, so therefore it is partially non-excludable, okay? And also, if it turns out to be knowledge, then it becomes non-rival. So these would allow us to stand on the shoulders of giants, okay? So we can really learn. Okay? Sustainable growth comes from non-rivalry and partial excludability, okay? And after the first creation, which sometimes could be very costly. It's like develop some drug, right? It's very costly, okay? But then an item, like a medical drug or an idea can be easily copied, shared, adapted, and improved, okay? So that's where growth comes from, okay? So this process of, copying, sharing, adapting, and improving not only apply to innovation in objects, goods, okay, but also apply to innovations in procedures, ideas, business models, legal systems, economic policies, urban management practices. Okay, so all of that. Okay, so we have a bunch of examples here, like assembly lines, just-in-time manufacturing, etc. So you have business models such as YouTube, Uber, Airbnb, okay? We have lots of copycats, right? Well, sometimes the copycats are doing better than the original idea originators, okay? And finance, okay? 蚂蚁金服, right? Using big data successfully, okay? But then soon can be copied by others, okay? So Paul Romer tried to make use of his theory. Okay, so he started this company, okay, called Aplia. Okay, it is a education website. Okay, so once you develop that, then it allows students to come in and log in and do review and problem set. Solve problem sets and submit it. So the platform can allow you to expand. Okay, so initial developing cost is high, but then the user cost, per user cost is really low. So he found this one and successfully, and now acquired by Cengage Learning in 2007. Okay, so. I recently checked into that website. It shows that there were like more than 2 billion answers submitted. Okay, so that's one. That's a business adventure, okay, by Paul Romer. And the Charter City was another of his ventures. Okay, so he gave a TED lecture in 2009. Okay, talking about this idea, right? So the idea is, if you have a developing country here, you set aside a piece of land, okay, and then, you introduce rules and regulations of the advanced economies, and maybe even invite some advanced economies to come in and actually be in charge of that piece of land, okay. So then you allow your citizens to opt into or out of that piece of land. Okay, so depending on whether they think it's good for them, right? So it's a very attractive plan. Okay, the only problem is that there's this connotation of colonization. Okay, so there are a lot of resistance by the developing countries. But one of them decided to have a try. So Honduras invited, Paul Romer to form a committee called Transparency Committee. Okay, so 5 people. In fact, some of the members are from Hong Kong, because Hong Kong and Shenzhen were considered to be model cities by Professor Paul Romer. Okay, so one of the member of the Transparency Committee was Victor Feng. Okay, Lian Feng Company, from Lian Feng Company. All right. So everything looked good, and they already chose the piece of land, and things are moving. But then suddenly, Paul Romer and his committee members, published an open letter and said, we're leaving. Okay, so this has nothing to do with us anymore, because that committee, okay, even though it was agreed by the president, and the president actually signed it, but it did not pass the, the legal system. Okay, so they decided to pull out. Right. So it's a pity that this trial did not succeed. Okay. So if this one, got off the ground, then it can be, if it's successful, then can be copied and extended to other developing countries. So I'm still hoping that someday that some city will, or some country will be willing to try it again. Okay. And policies, for example, the so-called inflation targeting framework invented in New Zealand in 1989. And then after it was successful, then it was copied by 28 other countries subsequently. Okay. Urban management practices. Okay, so that's what Paul Romer is trying to push now. Okay, that is to learn from history. Okay, and see the importance or power of the grid, which means the large boulevard that is set aside, okay, the public space. Okay, so how to design and how to make sure you set aside the public space first, and then allow the private land to be developed by others. But then they can never be allowed to invade into those public spaces, because those large boulevard later on would be needed to transport workers, staffs quickly through the traffic. So that's something, that's a project that he's working on now. Okay. And Paul Romer also mentioned in one of his presentations about this process of coding, publishing, and decoding. Okay. So through this coding process, people convert an invention, a new finding, a new procedure, a new idea into codified knowledge. Okay? So after you form the codified knowledge, and then can be published, and then be accessible, by many, many people. Okay? So that's, the spread of knowledge, spread of know-how that can promote economic growth. Okay? So those people who, saw this codified knowledge, and then they will have, have a learning and decoding process, okay, to turn the knowledge, for their own use. Now, thinking about this process, then you can see an extra effort, okay, spent in the coding process, okay, would give huge benefit to society. Okay, so when you do the coding, only a small group, maybe a single person, okay, who spend time, write and revise his paper. Okay, that's what Paul Romer did when he wrote his research papers, right? Writing and rewriting, okay? But then if you spend an extra hour in that process, it would make the decoding process much easier. And there are so many people who need to decode that message, right? So those would be the people who benefit from that, okay? So for that reason, Paul Romer actually, criticized some of the practices in economics, okay? So he had a paper about, the mathiness in the theory of economic growth, okay? This doesn't mean that he doesn't like math. I mean, you will see that he uses a lot of math, okay? But what he doesn't like is when people become sloppy, okay? The mathematical notion do not really correspond to the economic meaning that they represent, okay? So that makes the decoding process much difficult, okay? So he raised this criticism, and of course, became quite unpopular, okay? And also when he was the chief economist for the World Bank, okay, in 2006 and 2008, he pushed the staff to write more concisely and to the point, okay, and sometimes forces them to revise and cut the number of words, and, you have so many and this and that, long sentences. So that also caused those, World Bank staff very unhappy, okay. So eventually Paul Romer quit the World Bank, okay. So those were the main ideas, okay. But I think I still need to present some technical background so that you see, how difficult it was to actually come up with those ideas, okay. Now the two basic assumptions in macroeconomics, one is the aggregate production function, okay. So we write the total output as a function of capital and labor, okay. And this A, we call it, the level of technology, okay. So that's, the aggregate production function. And then we often assume that they exhibit constant returns to scale in capital and labor. Okay, so the idea is, if you have a company here, okay, with a blueprint represented by this A, okay, then you can also set up a copy of that company, okay, use the same machines, same floor space, same amount of labor, then you should be able to produce twice the amount of output, okay? So it has constant returns to scale in capital and labor, okay? And the other one is the marginal analysis, okay? That is, the returns to capital, okay, is equal to the marginal product of capital, and the return to labor, which is the real wage, is equal to the marginal product of labor, okay? However, once you have these two assumptions, then you can derive and prove that output will just be enough to cover for input costs of capital and labor, okay? So Y equals this. So therefore, there's nothing left to pay for innovation in technology, okay? Or even pay for knowledge, pay for technology, okay? So how could the economy grow? I mean, how could this economy function, right? Okay, so one way is, the simple way that is adopted by Robert Solow, another Nobel Prize winner. He would say, well, technology A is exogenous, okay? It just comes from the sky, okay? So, I mean, you don't have to pay for it, okay? And, this A actually grows exogenously over time, okay? So then, so this theory is called exogenous growth theory. Okay, we can say it's just a way to avoid the problem. Okay, it doesn't really solve the problem. It doesn't really tell us, what are the determinants of economic growth. Okay. So Paul Romer in 1986 was saying that, well, A is external to capital. Okay, so you have a piece of machine there. So whenever you have a new piece of machine, then it contains some knowledge. Okay, it generates this positive externality for other firms, in their development of technologies. So if it's external to K, and so therefore we can write the production function. You still have this constant return to scale, f of K and L, okay? But then you have a factor A, which is like positively related to average capital stock in the economy, okay? So then we know that in equilibrium, this K bar will be equal to K if we assume that all these firms were identical. So then the production function becomes Q of K and L, and then this function can exhibit increasing returns to scale in capital and labor, and therefore making growth sustainable. Okay, so this is so-called endogenous growth. Okay, endogenous growth, but still, it just rely on this story of externality, and probably we can say, well, it is endogenous, but it is not very sophisticated endogenous growth models. Okay, but because it is the first paper who talks about the endogenous growth, and therefore it attracted so many citations. Okay, more than 25,000 citations according to Google Scholar. Okay, so Lucas, the Nobel Prize winner, so he had a paper in 1988, JME. So he changed the production function as this. Okay, so it's a capital and efficiency labor. Okay, efficiency labor. So H is the human capital. Okay, so if you have higher human capital, then your productivity is higher. Okay, it's like effectively you have higher amount of labor. Okay, so L is just the labor, H is human capital, and U is the amount of time that you spend in production. And 1 minus U, that's the other time you use to accumulate human capital. Okay, so although he also assumed some kind of externality, but that's not the important part. The important part of the story is that human capital can be accumulated through schooling. Okay, through schooling. All right. So in Lucas' paper, the human capital accumulation is the one that really drives the economic growth. Okay, making it possible. Okay. So what is Paul Romer's contribution? Okay, Paul Romer, JPE 1990, endogenous technological change. Okay, that has been translated into many different languages. Okay. So in this paper, he would assume that output is a function of, HY, which is the managers, okay, number of managers, and L is unskilled labor, and all these XA is the amount of equipment of type A. Okay, and then there's also constant return to scale because alpha plus beta plus gamma equal 1. Okay, so if you double HY, double L, double all these XAs, you would double the output. Okay, so he also has constant return to scale. Okay, but then this A here, A would be produced in the R&D sector. Okay, so there's an R&D sector. So A dot equals delta times HA times A. Okay, so this H, so you have a total number of human capital H. Part of that were managers, and part of that were researchers in the R&D sector. Okay, and delta is a productivity parameter. Okay. So HA is the number of researchers, right? So the fact that you have A here, that means you are standing on the shoulder of giants. Okay, so the productivity of the PhD nowadays is much higher than productivity of PhDs 100 years ago. Okay, because the existing knowledge base has increased. Okay, has increased. So now there are also the specialized equipment producers. So each equipment producer, after purchasing a design from the R&D sector, okay, so when a new design comes out, this producer will bid and buy the right to that piece of design, okay, and then they can charge a monopoly rental price to final goods producer. Okay, so they would rent it to these guys. Okay, but because they are the only one who holds this piece of design, okay, who bought this piece of design. So they can charge a monopoly price, okay? So the monopoly price that they earned, so the monopoly profits that they earned will be just enough to pay for those R&D firms who produce these designs. Okay, so this is all very nice, logically consistent. Okay? So therefore, technological change and growth rates are determined by technological parameters, okay, such as the number of human capital in this country, okay, and alpha and beta, these are in the production function, and the delta, that is the productivity in the R&D sector, okay. So they will depend on this, but plus also the preference parameters, okay, such as rho, which is the rate of time preference, okay, which measures how patient you are, okay, whether you discount, whether you would be willing to wait for 2 months in order to buy this iPhone, or whether you want to, stay overnight to queue and try to buy the iPhone in the first place, okay. So this rho and also sigma, that is a measure of how substitutable the consumptions across time, okay. So the technological change and growth are endogenous. Okay, so now we truly have an endogenous growth model that captures the main elements of economic growth. Okay, so looking into the future, the implications of Paul Romer's theory. So now we have easy access to knowledge. Okay, so you have your mobile phone, you connect to the internet, easy access to big data, face-to-face communication. You communicate with your parents, communication with your collaborators. Okay, just use a mobile phone. Okay, so it's very easy, and instant translation. Okay, so that allow collaboration between scholars speaking totally different languages. If I want to collaborate with a Russian, now I can probably do it. Or in the future, near future, I can probably do that, even if he doesn't speak English. Okay. So in terms of the model, that means the productivity in R&D, this delta will be much higher. Okay, will be much higher. And also, this will lead to a globalized talent market. Okay, so once we can easily collaborate, it is as if we're in one country. Okay, we're working together. Okay, so HA will be higher. When HA is higher, then the growth will be higher. Okay, so the theory also support economic integration. Okay, the European integration. Okay, they wrote a paper in 1991 supporting that. And the Belt and Road Initiative that China is pushing, okay, and the integration among the Greater Bay Area. So this is the new thing here, and I predict that this will be the next big thing. Okay, the Greater Bay Area will lead to higher growth. Okay, the big question. Okay, so that's my own. What will the world look like when all these robots with artificial intelligence, like DeepMind, for example, start their independent quest for innovations? Okay, when they stand on the shoulders of not just human giants, but also robot giants. Okay, so what will be left for us, for humans, to do? Okay, when they started to pick up innovations. Okay, so will the merge of human and robot be inevitable? Okay, and in what form? Okay, so you're probably young enough to see that day, but some of us might not be able to see that. Anyway, thank you very much. Thank you.
Okay, thank you very much. I have a question about the excludability.
Excludability.
Yeah, hard word to pronounce.
All right.
So it basically means this piece of human capital or whatever, you can block it from other people from using it.
Yeah.
But
if that's the case, that's maybe partial excludability. Okay.
Yeah, right.
Okay.
And the knowledge that Professor Roma want to capture its property is non-excludability, right? So my question is it in this highly specialized knowledge world today, many knowledge may not be excluded from other people from using it, but in effect, it has much resistance for other people to using it. So you have to learn a lot to really understand what that piece of knowledge is about.
Right.
And the investment of this learning process also increases.
Right.
Either you can say the education cost or maybe just the human capital needed to learn it.
Yeah.
So is that consideration currently incorporated in our analysis of this whole growth process?
Okay. Now, if we wanted to help the society to improve and grow, okay, then what we should do is to make the knowledge more codified and easily codified or easily decodifiable, okay, so that people can learn it quickly, right? What you are saying was actually, well, sometimes the private R&D firms, they probably wanted to hide the trade secret, okay? They want to make it as difficult as possible so that people will not be able to learn quickly and be the easy copycat, right? Okay, so there is some conflict between the social objective and the private objective, okay. But what Romer says is that you still need to have a protection or legal protection framework, such as the intellectual property rights protection, okay, so that the R&D firms will be able to make some profit, at least for some time, okay, so that they have the incentive to innovate, okay. So he does consider those impacts, those aspects about the difference between social and between the private, and also he would say, well, sometimes you need the government intervention to make certain knowledge more transferable to others. For example, if there's an invention of a drug, okay, that can cure certain cancers, right? So then from the private objectives, then you should hold on to that piece of patent or secret for as long as possible so that you can make huge profit. But then from a social point of view, then Paul Romer would suggest that the government actually buy out, okay, that patent and then make the drug freely accessible to all the patients. Okay, so there is a role for government to play. Okay, but he also emphasized the market and saying that the market is important for things to work. Okay.
Thank you. I have another question.
Yeah.
It's about from what I see in the current model, it seems we don't take into consideration about of people's beliefs, or you could say some kind of optimism in this economic growth or pursuit of knowledge, maybe. So what I want to ask is it possible to capture these kind of elements rigorously into the model, or we really don't have the right tool, or all these kind of elements are just not well defined?
Well, in fact, in growth models, it is possible to have things such as multiple equilibria, which are connected to what you say, beliefs. Okay, so if we all believe that the economy will be a booming economy, then we would start to invest a lot, which actually help the economy to prosper. Okay, confirming our initial belief. Okay, so that's one equilibrium. The other equilibrium would be suddenly we feel pessimistic, and we don't make any investment, and the economy collapses, which confirms our initial belief. So I mean, you could have beliefs that work into selecting different kinds of equilibriums. Okay, so in that case, perhaps the government can also play a role in kind of selecting one of the equilibrium paths that are healthier. Okay.
Thank you very much.
So models with beliefs and indeterminacy do exist. Okay.
Thank you so much for your speech. I have a quick question about some data in China. And they said that over the past several years, Chinese productivity is not increased a lot compared to its GDP growth. So do you have any hypothesis for this phenomenon?
You're talking about new normal?
About growth.
Right.
Yeah, okay.
So I think first thing to do is to analyze why China grows so fast, okay, in the first, say, 30 years, okay? So there we can say, well, first of all, China was very backward, okay, to start with, 1978, okay, when the reform started. So there were a lot of things you can borrow from outside, okay? So the existing knowledge in the Western world was just so much. So you can borrow from that and you can learn from that. So you can grow relatively quickly for the first 30 years, okay? But once you are getting very close to the frontier, and then you don't have too much you can learn from them, or that they are now afraid of letting you to learn, okay? Letting you learn. So they will try to protect their know-how. And then, so it's getting harder and harder for China to be able to achieve that kind of rapid growth, okay? So it is kind of natural. Actually, in my speech in 2011, I projected that China's economic growth will slow down by like 0.2% per year until like 3%. When we go to 2040, okay? So I was not surprised by this trend of slowing down, okay? In fact, I think we should be happy that we still have like 6 point something growth nowadays, okay? So it is rather consistent with my predictions so far.
I was just wondering, how can this theory be related to the Greater Bay Area? So I saw your last slide, you talk about Greater Bay Area.
Well, because it promotes integration, economic integration, right? So when you can combine, the Greater Bay Area, so if before, you're doing your own R&D, I'm doing my R&D, and Macau is doing their R&D. So now we can combine them. So now you have like H1 plus H2 plus H3. So then you can allocate a larger number of human capital to R&D, and therefore economic growth will be higher. That's just a simple integration story. Okay.
On that note, I just want to pose a question. People talk about integrating universities too, right? Merging all the universities in Hong Kong so that there's only one university, and then there will be the ranking will be much better than each separate one, right? So is this similar to what you're talking about?
Oh, I think that's different. It's a bit different. Merging university. I think there's always some kind of limit to all these integration, right? So, because you also need coordination. And the larger that the university gets, the more difficult coordination would, the more costly would be the coordination. And also people might be arguing with each other a lot and say, well, why your school, getting so much funding and mine doesn't get? So there will be probably more infighting. But also, I think the competition among different universities would be important, so that we will continue to to do our best research, rather than just sit back and enjoy the no competition environment.
Yeah, for those who are so young, right? Many years ago, there was someone proposed to merge Chinese University and University of Science and Technology. So UST and CUHK to be merged into one. So at that time, it was about more than 10 years ago. So there was a big debate, I remember, okay? So it's kind of related, right? When do you have competition and when do you want to have integration, okay?
Right.
All right. Any other question? Actually, Danyang didn't mention in his talk, he's the first Paul Romer's doctoral student, right? First, is it?
Not the first.
Not the first?
But those,
This one behind you? I mean, before you?
There's a Japanese before me, but
Okay.
I think I was with him the longest time.
So,
Yeah. I followed him from Rochester to Chicago to Stanford. So.
and actually, Paul came to Hong Kong how many times? At least twice.
Several times.
Several times, okay.
Several
And
times.
Danyang hosted him. So actually, Paul was very attracted by Hong Kong's development.
Right.
It's very fascinating to him how could such a resourceless place could rise to the top in such a short period of time. So he looked at Hong Kong as an experiment, which stimulated his charter city idea.
Right.
So for all these stories, you can ask Danyang, okay, Professor Say, okay, he can tell you all these personal stories about Paul's visit to Hong Kong.
All right. So I do have a Chinese blog. So I wrote an article there. You can read. Perhaps some of you have already read. It has been read by 40,000 people in my own blog, but also through other networks.
It's in Chinese.
It's in Chinese.
Okay, good. All right, so if you don't have any more questions, there's a reception out there, right? So you feel free to continue the discussion. Thank you, both professors, and thank you for coming.
Okay, thank you very much.